Hi everyone. In this lecture on analog integrated circuits, we will look at how to draw the transfer characteristics of a CMOS buffer shown here. Now we are familiar with the CMOS inverter with a PMOS pull-up device and an NMOS pull-down device. Now what if you interchange both the devices? What if we interchange the PMOS with NMOS and NMOS with PMOS? Then we end up getting a buffer. It's a CMOS buffer. Now this characteristics, the transfer characteristics of this circuit is quite interesting. So I thought I'll just quickly discuss how to plot and how to intuitively or rather look at the transfer characteristics of this circuit in more detail. Now the transfer characteristics of a CMOS inverter is well known, so I'll not spend much time on that. So first, if I assume the input to be 0, the NMOS is cut off and only PMOS is on, so it's going to pull up this output node all the way to VDD. Now, if you slowly increase the input from 0 to VDD now, as you increase it from 0, the moment your input touches VTN, the NMOS will start conducting. Now, NMOS device will be in saturation region. The instant you cross VTN, NMOS will be in saturation. PMOS, it's in linear region or ohmic region because its VDS is very small, so it's going to be in ohmic region. And NMOS will be in saturation. So it will be the gain will now, the output voltage will start declining very fast because NMOS is going to behave like an amplifier. Even for a small incremental increase of delta V, output is going to fall down very quickly. It's going to behave like a current source which is draining the output node voltage. So that's why we see the voltage decreasing here. The slope will be quite steep. It will keep decreasing and decreasing, and then we'll cross the point called switching threshold, at which point as this output node voltage starts decreasing, your PMOS will also enter into saturation. So there will be some region in the transition region where both the devices will be in saturation. The gain will be even higher gain will be very high at that point. And there will be one point which we normally define as a switching threshold where the input and the output voltages are equal. Because your input is increasing, output is decreasing. At some point they both will meet, the output and input voltages will be equal, and that's called the switching threshold. If your devices are sized in such a way such that the mu and Cox W bar of NMOS and PMOS are the same, that point will typically be at VDD by 2. And also VTs of NMOS and PMOS are same, it will typically be at VDD by 2. And after that, as you keep increasing your input further and further, and when your input reaches VDD minus mod VTP, your PMOS is completely cut off. So as your input starts increasing further and further, NMOS VDS is decreasing, so NMOS device will slowly enter into linear region, and PMOS at this point, when your input reaches VDD minus mod VTP, will go into cutoff, and after that the output will be pulled down to ground by NMOS. It will go to 0. Okay, so this is a well-known graph, I think well discussed in most of the textbooks. So this is the characteristic of a CMOS inverter. If input is 0, output is VDD, and when input is VDD, the output goes to 0. And you have a transition region, a high gain transition region in between. Now what about the transfer characteristics of a CMOS buffer which is shown here? Where in place of a PMOS device, I have an NMOS device, and in place of a NMOS device, I have a PMOS device. So first, I will draw the transfer characteristic assuming that the minimum voltage the output can go to. So let's assume I'm going to keep my input at 0. So then initially, let's assume the output was at VDD. It's the PMOS which is going to behave as the discharging path. And when the output voltage reaches mod VTP, that being the threshold voltage of the PMOS device, after that the PMOS goes into cutoff and there is no other path for discharge. So minimum voltage I'm going to assume is mod VTP. So I'm going to assume your input can change from 0 to VDD. That's the range of voltages for which your input can change, and we'll also draw this graph assuming your input can change over a larger range. So first we'll make this assumption and draw the graph. So for the output here is initially at mod VTP and the input was 0. At 0 volts the output was at mod VTP. So this is where we are starting. So initially it is at mod VTP. Now if you start increasing the input node voltage, since it's a buffer, so how can you see it's a buffer? It's like you can see there are two common drain configurations connected in parallel. So this is a NMOS common drain, this is PMOS common drain. You've connected the two in parallel, so it will look like the output and input will be in same phase, which means if input increases, output should also increase. The opposite of CMOS inverter. So as I keep increasing the input voltage, the output stays at mod VTP. For the output to increase, if the output has to increase, the only charging path in the circuit is through this NMOS. So this NMOS has to conduct. Only then you'll have the output increasing. If the source terminal is at mod VTP, for this NMOS to conduct, the gate should be a VT higher. So which means if your input is starting from 0, only when your input reaches mod VTP plus VTN, the output starts to change or output starts to increase because the NMOS device here starts conducting. So until then it will stay at mod VTP. Now after that you can ignore the PMOS part because your PMOS gate voltage is higher, source is at your gate voltage is always at a higher voltage, so it won't conduct. It's higher by VT at least, so this device will not conduct. So it will only look like, the circuit will only look like something like this. So you have now a voltage given by mod VTP plus VTN, and the output voltage is at mod VTP here, and this node here is at VDD. Now if I increase this node voltage in excess of delta V, okay, so this PMOS will charge this node to VTP plus delta V. You can also see it like a common drain amplifier. If you increase this, because your current is constant, here your current is 0, so therefore if you increase this by delta V, this node voltage will raise till a point where the charging current goes to 0. So I am plotting the DC transfer characteristics. So it will go to 0 when this node output voltage reaches mod VTP plus delta V. So, and the slope, if you see, the input is changing by delta V, output is also increasing by delta V, and you can also see it's a common drain amplifier, so the gain will be 1. So it will keep on increasing. And when the input reaches VDD, the output is going to be at VDD minus VTN. So it will keep charging it till VTN, and after that this NMOS goes into cutoff, so it will no longer conduct. So the graph is going to look something like this. So it's going to increase linearly with a slope of 1, and when your input reaches VDD, it's going to stop at VDD minus VTN. And I'll probably plot the graph till VDD. So when your input reaches VDD, it's going to charge to this point and stop there. Now I'll decrease. Now the output is at VDD minus VDD minus VTN, and input is at VDD. So you can see it's a buffer. So input is increasing, output is also increasing. Now I'm going to decrease the input from VDD to 0. As I decrease my input, you can see now if the output is decreasing, the input is decreasing, output should also decrease, which means there should be some discharging path. For the output to decrease, there should be some discharging path. The only path for discharging here is through PMOS. Now we know the source voltage of PMOS, which is at VDD minus mod VTN. Now for this PMOS to conduct, the gate voltage should be at least 1 VTP lower than the source voltage. So until then it's going to remain constant. So it's going to remain constant till VDD. So the source voltage is at VDD minus VTN minus mod VTP. So it's going to remain constant till VDD minus of, so I can write it as VDD minus of VTN plus mod VTP. So it's going to remain constant for the same for the range of this range of voltage here. This range here will be VTN plus mod VTP. Okay, it starts from VDD till you reach this voltage VDD minus VTN plus mod minus of VTN plus mod VTP. It's going to remain constant. After that, your PMOS will start conducting. So now, since it's a discharge path, your NMOS will always be at cutoff. So we can ignore the NMOS here. So since only we are interested in the discharging path, NMOS takes there is no discharging in the NMOS path. So, and NMOS will not conduct because your gate voltage will always be lower than the source voltage. Okay, so since the gate is always lower than the source, NMOS anyways is not going to conduct. The opposite was happening when we were charging from 0. Okay, so the opposite was happening. The conduction happened after your gate exceeded the source voltage, and we saw how the graph looked like. Now I'm going to plot this response with PMOS in mind. So here the output is at VDD minus VTN, and the input here is at VDD minus of VTN plus mod VTP. After this, any excess decrease, say if I am decreasing it by delta V minus delta V, output will also decrease by the same amount. So this node will discharge till output goes to minus delta V. So the slope here you can see is 1. So if your input is decreasing, output is also decreasing by delta V, and it will keep on decreasing and decreasing. At when input goes to 0, the output voltage will discharge to mod VTP and stay there. After that, there is no discharging path, PMOS goes into cutoff. So this is how the graph will look like. An interesting observation to make here is that there is a built-in hysteresis in the circuit. As your input voltage increases, the point where the tripping, where the transition happens is different when your output voltage is, when the input voltage is changing in the opposite direction. So there is a built-in hysteresis in this circuit. Okay, and this region here is the width of this region in voltage terms is VTN plus mod VTP, and this is slope is 1. Okay, so that's how this graph of a buffer is going to look like if your input is going to go from 0 to VDD. But how will this graph look like if the input were to go from, say, minus infinity to plus infinity, or in a large negative and positive voltages? I'm not worried about breakdown right now. I'm just going to change it to lower than 0. The input can go lower than 0 and higher than VDD. It can go higher than VDD and lower than 0. But I'm going to assume supply is at between 0 and ground. That is between 0 and ground. But input can go higher than VDD and lower than 0. And in that case, how will this graph look like? So to plot that response, now we'll revisit our initial assumptions. So which is initially, if I assume this node to be at 0, we said that output can be at mod VTP because your PMOS discharge path becomes inactive. After that, the device goes into cutoff. But if your input can go to lower voltages, then of course there is sufficient VT for this PMOS to conduct, so output will also decrease. So we said if your input was 0, we were at mod VTP. But now I'm saying we can decrease input further. So of course it's going to be in saturation because it's always 1 VT lower. So the input will decrease, output will decrease. And at some point when your input reaches minus mod of VTP, your output will go to 0. So this is the point. So it will be when input reaches minus mod VTP, your output will go to 0. So that's where we are at. So your input is at minus mod VTP now, and the output has gone to 0. So now I'll increase from minus mod VTP to all the way to VDD and a voltage higher than VDD, and we'll see how the graph looks like. So first, output is at 0, input is at minus mod VTP. I am now increasing the input. If I am increasing the input, you can see PMOS is anyways cut off, because if your gate is increasing, source is at your gate and source were already separated by 1 VT volts, but now gate is increasing, so PMOS is already going to cut off and deep cut off. But now there are chances that NMOS can enter in. It is already in cutoff, but it can enter into saturation. So since the input is at 0 now, the output is at 0, if the gate reaches 1 VTN volts, then this NMOS will conduct. So the graph will look something like this. As your input is increasing, here from 0, the output will stay at 0. So I am plotting it here. Okay, input is now going from minus VTP, and when it reaches VTN, your output starts to rise, because your NMOS will conduct. So initially is at 0, input has reached VTN, and this is at VDD, this is at 0. At this point it will start conducting. So you increase this by a delta V, output will also increase by delta V, because until it reaches delta V, it will keep on charging, it will keep on providing some charging current. When the output becomes delta V, then you have 1 VT, you just have 1 VT across the PMOS and NMOS, and it will no longer conduct. So output is going to increase. So it's going to increase with a slope of 1. So for a delta V increase in the input, there is a delta V increase in the output. So it will keep increasing. At V in equal to VDD, you are going to reach a voltage of VDD minus VT. So that's what we did already. So this was going to VDD minus VTN. But I am going to increase input further. I am going to increase your input to say VDD plus VTN. I am going to increase it to VDD plus VTN. At that point, your output node voltage can go as high as VDD. So it can go as high as VDD itself. So I am increasing it to VDD plus VTN. It can go as high as VDD. And after that, your PMOS device will enter into linear region and cut off, because what will happen is there are two ways in which an NMOS device can carry zero current. One, it can have a finite VGS. So if you look at the IV characteristics, so this, if you have your VGS is finite, you can make the current in a MOS go to 0 if its VDS is 0. So this is the operating point. The other case is you can have a finite VDS, but if your VGS is less than or equal to VTN, then even then you can have the current going to 0. So that will be in cutoff region. So there are two possibilities. What will happen here is that after your input exceeds VDD plus VTN, even though your MOS device can charge to higher voltage, the drain voltage will limit it. It will limit it to VDD. So it will stop at VDD. So the graph will look like this. It will stop at VDD and it will remain constant. So right now, I am not worried about breakdown. So here if you see, gate to drain voltage might keep increasing. I am not worried about that. Okay. So breakdown, we are not worried about it. We are just drawing it using the simple square law model. The characteristic will look like this. If you keep increasing your input, or maybe within some reasonable limits, the graph will look like this. Now we'll come back in the opposite direction. So we are at a point where the input voltage, the output voltage is at VDD. Input is at a much higher voltage than VDD. Now we'll keep decreasing the input. Now if you are expecting the output to decrease, that will happen. It means there has to be some discharge path, and that has to be through the PMOS device. But for the PMOS device to conduct, the gate should go 1 VT lower than the source. Now since source is at VDD, the point where your PMOS device will start conducting will be at VDD minus mod VTP. So I am now decreasing my input. I am decreasing my input here. So this is the direction in which I am coming. Output stays at VDD because there is no discharging path. But the moment I reach, so this is VDD plus VTN, I've crossed that point, output is still staying at VDD. I've reached VDD, but even if I'm at VDD, there is no sufficient VT for this PMOS to discharge, so it's going to remain constant. I have now reached a point which is VDD minus mod VTP. At that point, the device PMOS starts to conduct, and after that it's going to have it's going to conduct after that, and it will have a slope of 1. PMOS will discharge it with a slope of 1, and it's a PMOS will be in common drain configuration. So the graph is going to look like this. So this is how the graph will look. So probably it's not drawn properly, but I think you get the picture. So if you increase it in this direction, it will go with a slope of 1, and when you decrease it, it's going to follow a different path. So there will be a hysteresis here. So it will decrease in this direction. So if you increase your voltage, it's going to go in this direction, and when you decrease it, it will trace this path. Okay, so that's how you draw the transfer characteristics of a CMOS buffer. Thank you.